Very good morning to everyone. Myself, Dr.P.SEVVEL, Professor, Department of Mechanical Engineering, SC Engineering College, an autonomous institution affiliated Anna University, CHENNAI 77. In today's GATE coaching class, we are going to see the topic casting technology. So moving on to that, before starting the casting technology, I want to give you a short introduction about the pattern which is going to be followed in the GATE Mechanical Engineering question paper pattern 2024. So if you are going to see this pattern, so the duration is going to be totally 3 hours. And the type of questions is going to be of 3 different types. First one is going to be multiple choice questions, that is MCQ. Second one is going to be MSQ, that is multiple select questions, in which you are going to have 2 or 3 more answers which are going to be correct. And last one is going to be numerical answer type. And the total number of questions which are going to be asked in mechanical engineering stream is going to be 65. And the total awarded marks is 100. And you are going to have total number of sections. The total number of sections is going to be either 2 or 3, which is going to depend upon the paper. And if you are going to see the GATE section wise number of questions, in general aptitude you are going to have a total of 10 questions, and in core discipline you are going to have a total of 55 questions. So out of the 65, 10 is going to be from general aptitude and 55 questions are going to be from the core discipline. Next, GATE section wise weightage, if you are going to see, GATE general aptitude is going to have a total of 15 marks out of 100, and remaining 85 marks goes to the core discipline. So the marking scheme, you are going to have negative marking also, as you are going to see over here. So for 1 mark multiple choice questions, 1/3 mark will be directed for a wrong answer. This is going to be the pattern which is going to be followed for GATE Mechanical Engineering in the year 2024. So now we are going to see the mechanical engineering syllabus for the GATE and the weightage for each and every topics. So if you are going to see the mechanical GATE engineering syllabus, it is going to have general aptitude, which is going to have a weightage of 15 marks, followed by engineering mathematics, which is going to have a weightage of 12.25 marks, then engineering mechanics 2.5 marks, strength of materials 7.75 marks, heat transfer 6 marks, and you are going to have machine design, fluid mechanics, theory of machines, thermodynamics, refrigeration and air conditioning, industrial engineering, and finally manufacturing engineering. And if you are going to see this, out of all these topics, manufacturing engineering is going to have the highest weightage of marks, and it is going to be 14.25. So we are going to discuss the topic manufacturing engineering. So I am going to cover the various topics which are going to come under the manufacturing engineering stream. So as a part of the manufacturing engineering, which is going to have a weightage of 14.25 marks, we are going to see the first topic, which is going to be called as a casting technology. So directly going on to the question, we are going to have some 2 or 3 slides which is going to give you a small and short introduction about casting technology. So if you are going to see the casting of metals, so as you already know, the casting is going to be one of the very renowned term in engineering, especially with respect to mechanical engineering. And casting is a process in which the molten metal flows by gravity, majority by gravity, and into a mold where it will get solidified in the shape of the mold cavity. So the casting is going to be a process in which the metal is going to be melted and it is going to be poured into the cavity, in which it will take the shape of the cavity. And the various steps in casting, it is going to include melting the metal. So first the metal is going to be melted, second is going to be it is going to pour into a mold, and finally it is going to be allowed to get solidified. This is going to be various steps in casting. So if you are going to see here you can see the basic arrangement of sand casting process. As you can see over here, it is going to be cope and drag arrangement, in which the molten metal, as you are going to see, it is going to be in blue color, is going to be poured over here, and it is going to pour through the pouring basin, and it reaches the cavity where it is going to take the shape of the mold. So this is about the short definition of casting process. So what are all going to be the capabilities and advantages of casting? So if you are going to see that, the most unique advantage of casting is that we can create complex and intricate shapes and structures. So the structures which are difficult to get manufactured by other processes like forging or extrusion, etc., can be easily fabricated using this casting process. So complex, irregular, complicated shapes can be fabricated very easily using casting process. That is going to be the first advantage. You can create both internal structures as well as exterior structures. So the structures which are going to have internal geometry and those geometry which are going to be very much complex, that can be very easily fabricated using this casting process. Next, very huge parts, large size parts can be fabricated very easily using this casting technology. And finally, it is going to be suitable for mass production. So we are going to produce 100 number of similar parts 500 number of similar parts or even 1000, 10,000, etc., the casting is going to be the most suitable technology and it is going to be very much suitable for mass production. What are the parts which can be made using this casting technology? So here you can see the photograph of various automobile parts which are fabricated using the casting technology, and as you can see in this slide, very big parts of automobiles including engine blocks, heads of automotive vehicles, then wood making stoves, railway wheels and various parts of the railway coaches, etc., are being fabricated using this casting. Apart from this huge size parts, small parts like dental crowns, even jewelry and frying pans, small statues, etc., are fabricated using this casting technology. So this introduction, we are going on to see in a detailed manner the previously asked GATE question papers on casting technology, which comes under the stream of manufacturing engineering. So we are going to see a total of 10 to 12 GATE questions which are asked with respect to casting technology, and we are going to see their answers and we are going to solve in a detailed manner so that everyone understands in a simplified manner. So the first question, this question was asked in the year GATE 2016. So the first question is the part of a gating system which regulates the rate of pouring of molten metal is option A, pouring basin, option B, runner, option C, choke, and option D, in-gate. So repeat once again, the first question was asked in the year GATE 2016 and the question is like this: the part of a gating system which regulates the rate of pouring of molten metal is, you are given four options: option A, pouring basin, option B, runner, option C, choke, and option D, in-gate. So if you want to understand the correct answer and if you want to identify the correct answer of this, you have to understand the concept in which metal is going to be poured into the mold and what are all the various parts of the mold you are going to see here. So now I am going to give you a clear detailed diagram illustrating the various parts of the casting mold. So this diagram will not be given in the question. The question completes with this. So like this, our question will be given. For your better understanding, I am giving a diagram so that a diagrammatic illustration will help the listeners to understand and identify the correct answer. So you are going to see this. So the various parts of the casting is going to be like this: pouring basin, followed by sprue, then choke, then runner, then in-gates, then the mold cavity, and finally the riser. So now you are going to see the function of each and every part which is going to be seen in the diagram. This diagram which you can see over here, you can see the various parts here. First part is going to be a pouring basin. As you can see here, the pouring basin, it is going to act as a reservoir. As you can see the pouring basin here, it is going to act as a reservoir for the molten metal. So the molten metal is not going to be poured directly into the mold, it is going to be poured through the pouring basin, as you can see over here. So the pouring basin is going to act as a reservoir for the molten metal. Second part is going to be sprue. The sprue is going to be the part through which the molten metal is going to be poured into the choke and then to the runner, as you can see over here. So the second part is going to be the sprue. The sprue is going to be the part through which the molten metal pours from the pouring basin to the choke. And here you can see the sprue, it is going to be taper in shape over here. Why it is taper in shape? If you are going to see that, if it is now instead of taper, it is going to be a straight passage, then low pressure intensity will be developed, and due to this low pressure intensity, air will get trapped inside the pouring molten metal, and the trapped air will lead to a lot of defects and impurities. So in order to avoid the air to get trapped inside, instead of this straight channel, you are going to reduce the size of the length of the channel in such a way that it is going to be in the form of a taper. So as you can see over here, the sprue is going to be tapered. Next, choke. If you are going to see the choke is going to be the control area which is going to be placed at the bottom of the sprue and is going to be called as the sprue well. And by placing the choke, we are going to control the fluid of the metal flowing into the mold cavity so that the mold is filled in calculated pouring tank. So the choke is going to be the control area, or is going to be the control limit, so that the metal which is going to be poured to the sprue are going to be regulated and it is going to be permitted in portions to the fill up the cavity. Next comes your runner. So if you are going to see the runner allows the molten metal to enter the cavity through the in-gates. Next comes your in-gate, the last point where the molten metal is going to enter the mold. That is going to be the in-gate. And finally the riser. The riser is going to act as a reservoir from which the molten metal can be drawn into the mold cavity as solidification contraction occurs. So this is going to be the last part by which overflow of the metal can also be retreated back, and in case of the molten cavity gets solidified, you can pour additional metal through the riser. So this is going to be the various parts. So now coming back to the question, as you can see over here, the part of a gating system which regulates the rate of pouring of molten metal is. So by seeing the diagram itself, you can understand what is going to be the part, and if you are going to see, the answer is going to be choke. Because pouring basin, as I already told you, it is going to be act as a reservoir of molten metal. It is not going to regulate the rate of pouring of molten metal. Pouring basin is going to act as a reservoir. From pouring basin is going to be poured through the screw, and the choke, as I already told you, it is going to act as a control area, so that it is going to regulate the volume of molten metal which is going to be poured through the screw and pouring basin, and then it is going to be transferred to the runner. So the ingates are nothing but they are going to transfer the molten metal from the runner to the mold cavity. That's all. The runner is going to permit uniform movement of the molten metal, so they are not going to regulate the volume of molten metal or rate of pouring of molten metal. So it is going to be the choke. So the correct answer for this question is going to be choke. So by seeing the diagram, you have got better idea what are all the functions of all other parts of the casting. So we are going to move on to the second question. The second question, if you are going to see that, it was asked in the year GATE 2017. So the question is like this: the allowance provided to a pattern for easy withdrawal from a sand mold is option A, finishing allowance; option B, shrinkage allowance; option C, distortion allowance; and option D, shake allowance. So this is going to be the question which was asked in the year GATE 2017. So to understand this allowance, you have to first see what is going to be the types of the pattern. So here I am going to show you the various slides in which you are going to have the various photographs of the types of the pattern. First one is going to be single piece pattern, two piece pattern, multi piece pattern, loose piece pattern, followed by cope and drag, then next sweep, next shell, next skeleton, then segmental, follow board, match plate and gated. And if you are going to see this casting, in casting what is going to be a pattern? Pattern is going to be very simple. In casting, a pattern is a replica of the object to be cast. So whatever shape of the object you want to produce through casting, that is going to be in the form of a pattern. So if you want to fabricate a pen like this, so the pattern is going to have the shape of the pen which you want to produce. So the pattern is going to is the exact replica of the product which you want to manufacture or which you want to produce. So that is going to be the pattern. So most commonly used pattern are going to be single piece or two piece followed by multi piece. Then other types based on the operation is going to be sweep, shell, skeleton, etc. So now in the question they asked about four types of allowance: finishing allowance, shrinkage allowance, distortion allowance, shake allowance, which is provided in the given pattern. So first we have understood what is going to be the pattern, and you have seen the various types starting from single piece, then two piece, multi piece, etc. up to gated patterns. Now we are going to see about each and every type allowance. So first, finishing allowance. This allowance accounts for the extra material that will be machined away to achieve the final dimensions. So after fabricating the exact shape of the product, some of the molten material will be extruding outside. So what we are going to do to avoid that, we are going to give a finishing allowance so that extra material which are going to protrude outside, we can be removed later using the machining process. Such type of the allowance which will be provided additionally for the molten metal to come out so that they can be protected outside and they will be remaining as a projection. That allowance is going to be called as your finishing allowance. Next, shrinkage allowance. Shrinkage allowance is exactly contradictory to your finishing allowance. Here the metal will get solidified and it will get shrink. So you have to produce an allowance such that it is going to compensate for that shrinkage. So that is going to be called as your shrinkage allowance. In simple words, the metal after solidification or after cooling will get shrinked in size. So to accommodate for that, you have to provide some allowance that is going to be shrinkage allowance so that you can compensate for the exact size of the product or exact size of the component which you want to fabricate. Next is going to be a distortion allowance. So distortion allowance is going to see that you are going to have some wrapping or distortion due to the casting process. So to avoid that, you are going to have some allowance that is going to be called as a distortion allowance. Distortion means some disturbance. So you are going to have a wrapping or twisting or distortion. To avoid that, you are going to provide allowance. Next, shake allowance. The other name for shake allowance is going to be called as your draft allowance. So if you are going to see that you are not going to provide exactly straight channels, you are going to produce slightly tapered, or you are going to produce an angled channel, so that the easy removal of the product after the casting process can be carried out in an easy manner, so that you can understand the shake allowance in such a way that you are going to remove the product by shaking, so that do the shaking process you are going to provide a taper angle, or you are going to provide a clearance in such a way that the allowance can be shaped, or the pattern can be shaped, and it can be taken out of the casting mold. So that is going to be called as your shake allowance. So based on this idea, you are going to see that the allowance provided to a pattern for easy withdrawal. So in finishing allowance and shrinkage allowance, we are not speaking anything about the easy removal. Finishing, metal is going to overflow. In shrinkage, metal is going to get solidified and is going to shrink. So to compensate for both of them, we are going to give some allowance. In distortion, it is going to have some disturbance. To avoid the disturbance, we are going to create some allowance. But in shaking allowance is the only allowance which is going to deal with the easy removal of the product from the casting, from the mold or from the cavity. So that is going to be the answer, and we are going to see that the correct answer is shake allowance, which is going to be option D. So the correct answer for the question is going to be that the allowance which is going to be given in a pattern for easy removal of the metal from the sand mold is going to be your shake allowance. So answer option is D. Next. So this is going to be a question which was asked in the year GATE 2014, and this is going to be match the taper columns. So you are going to have one column which is going to deal with the various types of the defects in casting, and another is going to be the column, the reasons due to which the defects occur. So I am going to read the question now. Match the casting defects, that is group A, which is going to be given in the column group A, with the probable causes, that is given in the group B. I am going to read it. Group A, RTS, shrinkage, blowholes, cold shut. And group B, the reasons: improper fusion of two streams of liquid metal, then low permeability of the sand mold, number 3, volumetric contraction both in liquid and solid stage, and number 4, differential cooling rate. So options are P, that is RTS for first one, then Q for 3, R for 2, S for 4, like this you are given 4 options. So group A, that is column 1, is going to be the defects. Column 2, it is going to be the reasons. So you have to match the defects with their proper reasons. Due to this reason, the defect is taking place. So now, to understand and to identify the correct answer, you have to first know about what are all the various types of the defects taking place in a casted product or in a casted component. So now I am going to give a diagrammatic illustration of various types of defects present in casting. First is you are going to see over here, this is shrinkage cavity, in which the component is going to have a shrink volume or shrinkage in size. So this is going to be the entire rectangle or cube which is going to be formed, but you are going to have a shrinkage. This is going to be called as a cavity, which is formed due to this shrinkage. And here you can see the RTS. Some portions have been teared down, so toned down, as you can see over here. This is going to be called as your art tears. And this is you are going to have some drops. So extra, this is going to be very much similar to a finishing allowance. So this is going to have some extra projection which is going to be called as your drops. Here you can see some blowholes. So as already told you, if the screw is not given a tapered shape, then automatically low pressure intensity will be created, due to which air will get trapped inside and it will lead to the blowholes like this. So this is going to be there. Then you are going to have the misrun. Some unevenly in extra projection has been found over there. Then this is going to be the metal penetration, as you can see over here. So this is going to be the various types of the casting defects. So now I want to show you a realistic photograph view of each and every type of the defects. So you can see the micro shrinkage here, then you can see the explosion penetration, then bone on, then broken mold. Here you can see the lustrous carbon inclusions. Unevenly carbon has been distributed over there. Then you can see a scar over here. A scar over here like this, which is going to be called as your scarred surface. Then you can see the blowholes here, which I have shown in the photograph. Now which I have shown as a diagram, now you can see in the form of a photograph. And here you can see the metal penetration. Then you can see some slag-like inclusions. Then here pinholes can be seen, and here you can see a rough surface, roughness. Here you can see some scabs, etc. So this is going to be the various types of the defects. So based on this, what is going to be the answer? You can see over here. So the answer for this is going to be option B. The answer for this is going to be option B. So you will be coming over here and again you will see what is going to be the option B. So option B is like this. So P is nothing but RTS. RTS go for differential rate of cooling. Whenever you are going to have a difference in the cooling rate, then automatically lead to RTS. So P is matched with 4, so that is going to be P is to 4. Then Q, shrinkage. You can see shrinkage with volumetric contraction. So contraction is nothing but shrinkage. So shrinkage is, reason for shrinkage is volumetric contraction both in liquid and solid stage. So here you can see over here. Then blowholes, it is going to be reason 2. So blowholes are caused due to low permeability of the sand mold. And final defect is going to be cold shut. The option is going to be 1, which is going to be improper fusion of 2 streams of liquid metal. So this is going to be the reason. For the reasons are matched with their correct defects, and you can see over here. I repeat once again, RTS are caused due to differential rate of cooling, followed by here Q, then blowholes, then cold shut. Next, question number 4. The question number 4 is going to be a problem which has been asked with respect to casting, as you can see over here. So I am going to read the problem again. So a true centrifugal casting operation needs to be performed horizontally to make copper tube section with outer diameter of 250 mm and inner diameter of 230 mm. The value of acceleration due to gravity G is 10 mm per second square. If a G factor, that is ratio of centrifugal force to weight of 60 is used for casting the tube, the rotational speed required is what RPM? That has been asked over there. You are asked to round up the digit. So now we are going to see the value first. So what you are going to find out? You have to find out the rotational speed required for fabricating this true casting type of the copper tube, which is going to be fabricated using the true centrifugal casting process. So here given value, outer diameter is equal to 250 mm, inner diameter is 230 mm, then acceleration due to gravity G is 10 meter per second square, and finally the G factor is 60. So if you are going to see that, first you are going to have so given diameter is going to be outer diameter, it is going to be D0 is going to be 250 mm. Inner diameter is less, and let us assume it is going to be DI, it is going to be it is going to be of 230 mm. So outer diameter is going to be 250 mm, inner diameter is going to be 230 mm, then acceleration due to gravity G is equal to 10 meter per second square, and capital G is going to be 60. So we are having a formula in casting, G factor, which is going to be the ratio of centrifugal force to weight, that is G is equal to F of C divided by mg. We know that force is nothing but F is nothing but mass into radius into omega square divided by, already you are having mass of m into g, so keep it as it is. So this is going to be the formula. So we are given G is 60, you don't need to bother about the inner diameter, you leave it as it is, because we does not need the inner diameter for this open centrifugal casting, we need only outer diameter. Then G is going to be there. So you are going to substitute as it is over there. So G is equal to centrifugal force divided by weight. Weight is nothing but W. W is nothing but M into G. So here, if you are going to see it as it is, here it has been written over here. So we are going to consider only the outer radius as it has been shown over here. Now G is equal to M R omega square by WG. I am going to write as it is. G is equal to M R omega square divided by mass into gravity. So what I am going to do, I am going to remove mass and mass. So you are going to have finally G is equal to R omega square divided by G. This is the final value which I left over here. So repeat once again, you are going to have G is equal to M and N will get cancelled, R omega square divided by G. We know that omega is equal to 2 pi n divided by 60. We know that omega is equal to 2 pi n divided by 60. So, and what is going to be radius? Radius is nothing but outer radius, it is nothing but outer diameter divided by 2. So, we are having the formula G r omega square divided by g, small g. So omega is 2 pi n divided by 60 and r is nothing but the outer radius. So outer radius is nothing but outer diameter divided by 2. So we are having the outer diameter is nothing but 0.25 meters. So this is the value. We are going to substitute it as it is. So r omega square g, what I am going to write? R I am going to write it as d naught by 2 into g. This alone I am going to write it over here. Then g I am going to write it as it is, omega 2 pi n divided by 60 the whole square, as you can see over here. And what is the value of capital G? It is nothing but 60. As you can see over here, it is going to be 60. So you leave it as it is. So from this, what you are going to do? You are going to find out n square. So what you are going to do? 60 is equal to d naught by 2. D naught is nothing but 0.25 divided by 2 into g. G is nothing but acceleration due to gravity 10 into 2 pi n square divided by 60 the whole square. So you write it again. 60 is equal to 0.25 divided by 2 into 10 into 4 pi square n square divided by 60 square. So you take 60 over here. So what will happen? 60 cube, it is equal to 0.25 divided by 2 into 10 into 4 pi square n square. So what now I am going to take? So n square is equal to 60 cube into 2 into 10 divided by 0.25 into 4 into pi square. You take finally n, you will get a value which is going to be equal to 661.93. Round it off, you will get 662 RPM. That is the answer you can see over here. So you are going to get a value of 662 RPM. So now moving on to the answer. So the answer is 662 RPM. You are not given any option A, B, C, etc. You have to write the final value. It is going to be 662 RPM. Now moving on to the fifth question. You can see over here again it is going to be the match the column. So you are going to have two columns. Here you are going to have various parts of the mode and here you are going to have their functions. It has been asked in the year GATE 2015. Now match the items in the first column to their functions in the second column. So first column you are going to have various parts of the mode: screw, riser, gate and pouring basin. And here you are going to have the various functions. First one, it regulates the flow of molten metal into mold cavity. Number 2, feeds molten metal from pouring basin to gate. Number 3, acts as a reservoir for molten metal. And number 4, supplies molten metal to compensate for liquid shrinkage. This is going to be the given options. So with respect to this question, you have seen question number 1 and question number 3, which deals more or less with respect to this. Based on the idea, I am going to give the answer. You yourself can understand. First, you already heard about this. If you have carefully observed this class, already we have spoken about this. Acts as a reservoir for the molten metal. So which is going to act as a reservoir for the molten metal? It is nothing but the pouring basin. So yes is going to be for 3. So you see the options now, which is going to be S is equal to 3. You are going to have two options. Option number B and option number C. So you can strike out option number A and you can strike out option number D. So you are left with the two options. You know only one correct answer. With that you are identifying, you are shrinking the options. Option B and C, because both are saying that the pouring basin is acts as a reservoir for the molten metal. It is going to be correct. With this, I am locking two options. B and C, remaining two are going to be wrong. You leave it. Now coming to the second. Next, It regulates the flow of molten metal into the mold cavity, which is going to be your one thing, and another is going to be feeds molten metal from the pouring basin to gate, and supplies molten metal to compensate for liquid shrinkage, which is going to compensate for liquid shrinkage. If you are going to see this, one is going to be riser, gate and sprue. You are having three options. So I am already given you the function of the riser. The riser is nothing but it is going to compensate for the liquid shrinkage. So Q goes for your 4. Okay. So in these options you see which is going to be 4. Then you are left with only one option, which is going to be the correct option. Q is going to be 4. So sprue is going to feed the molten metal from the pouring basin to the gate. As already seen the diagram. If you want to see the diagram, you can see here. So you can see the diagram. By seeing this diagram, you can identify very clearly the correct option is B, which says that P is going to be feeding the molten metal from the pouring basin to gate. So the sprue is going to be P, which is going to feed the molten metal from the pouring basin to the gate. It is going to feed it. And option Q is riser is going to 4. Here you are going to have the riser. The riser, as you can see over here, it is going to supply the molten metal to compensate for the shrinkage, liquid shrinkage. Next, you are going to have the option R1, which is going to be gate. Gate is going to regulate the flow of molten metal into mold cavity. Here you are going to have the gates. They are going to regulate the flow of molten metal into the cavity. And last, you are going to have the pouring basin is going to act as reservoir for the molten metal. So this is going to be the correct answer, which is going to be option B. And we are going to see the last question of today's class. With this, we will be completing our today's class. So you are going to see the last question, which is going to be again a problem, which is going to be asked with respect to casting. So you can see the problem over here. A cube-shaped casting solidifies in 5 minutes. It was asked in year GATE 2013. A cube-shaped casting solidifies in 5 minutes. The solidification time in minutes for a cube of the same material, which is 8 times heavier than the original casting, will be option A 10 minutes, option A 10, option B 20, option 3 24, and option D 40. Let us see the explanation over here. So I will be explaining everything clear. Okay. What is going to be the formula for time required for solidification is T is equal to C divided by V by A the whole square. So what is going to be your C here? You are going to have C. C is going to be a constant, which is going to depend upon the material which is going to be poured, and V is going to be the volume, and A is going to be the surface area. So we are going to have T is equal to C V by A the whole square. So already we are given for first cube the time taken for solidification is going to be 5 minutes. And we don't know what is going to be the weight of that, but it is given that second object is 8 times heavier than the first cube. So W2 is going to be 8 times heavier than W1. We know that weight is nothing but rho into volume into gravity. So rho Vg of second object is going to be 8 times the density into volume into gravity of the second object. So what will happen? Rho Vg of second object will be equal to 8 times rho Vg of first object. Here density, gravity will be common, so they will get cancelled. So what you will get? V2 will be equal to 8 times V1. That we are getting here. So this is with this we are arriving over here. Next, what is going to be volume? 3 times the area. So volume of second object is going to be 3 times the area of the second object is going to be equal to 8 times the area of the first object, 8 into A1 cube. So what is going to be A2? It is going to be 2A1. Area of second object is going to be equal to 2 times the area of the first object. This is going to be first set which we are giving the detailed explanation. Okay. So for the first cube, let us find out the time. Already we know time is going to be equal to 5. So we know the formula. T is going to be C into V by T is equal to C into V by A the whole square. It is given that time is going to be equal to 5. It is going to be equal to C. It is a constant. You keep it as it is because it is going to be a common term. You keep it as it is. Next, volume is nothing but A1 cube divided by 6 times the area of the first object. It is going to be the whole square. What you get finally? 5 is going to be equal to A1 square divided by 36 into C. So this is the first thing which is going to be equal to 5. Likewise, you do for the second cube, you will get finally this is going to be equal to T2. So this is going to be like this. So T2 by T1, what is T2? T2 by T1 is nothing but 4 by 1. I have written over here, because here you are going to have the option only 4, because A1 square will get cancelled, 36 and 36 will get cancelled, C and C will get cancelled, so you are remaining having only 4 and here will be having 1. Already we know that T1 is going to be equal to 5. So we are writing that T2 by 5 is equal to 4 by 1. T2 by 5 is equal to 4 by 1, so T2 is equal to 4 into T1. We know the time for first cube for casting is going to be 5 minutes, so 4 into 5 will get 20 minutes. So the correct answer is option B, which is going to be equal to 20 minutes. So with this, we are coming to the conclusion of the first part of the casting technology, which has been questions which has been asked on casting technology in the previous GATE year question papers. So in the next session, we will be seeing some more interesting questions which has been asked with respect to casting technology on GATE question papers. Thank you very much. Thank you.